but they persisted with it through a very long startup, 5 or 6 years to achieve design rate, which would have crippled any Western company. The ability to finance a project through a 5 or 6 year startup is incredibly difficult, and that sinks companies. And the new facilities that are being built are very successful, right? The only other company that's built more than one of these is in the Philippines. I got to own it. I know a lot about nickel and I'm pretty nerdy. 15 years from now, we'll probably have a 50-50 split of stainless steel and high purity stuff, mostly for batteries. For a commercial facility that's making 30,000 tons a year, you're probably going to need something like a 30 megawatt power generation facility. The real challenge is it needs to run all the time. These are not facilities that you can turn on and off. They need to start up and run for months at a time. One of the things that I talk about in this, Al, is highest and best use. The fuel uses, they're just not as important. It's not the best use for the materials.
Hey, I'm Al, and this is the Paglalayag podcast. I'm using this podcast to showcase what's going on around me in the hardware and clean tech sectors dito sa Philippines. With guests from across the startup, research, investment, and enabler ecosystems, Paglalayag focuses on the stories and inspirations that motivate us to start up in hardware and press on down this arduous path of steering our economy away from the looming climate catastrophe that makes itself increasingly felt in our lives each passing year. I hope you'll find this cast of characters as impressive and inspiring as I do. Also, if you've been listening to these podcasts and want to let me know what you think, there's a survey form available at paglalayag.net-podcast. You can also reach out by email at al@paglalayag.net. I'd love to hear from you. Sige, tuloy-tuloy lang. Let's jump in. Okay, so welcome to Paglalayag. I'm Al. And today, my guest today is Lyle Trytten of Trytten Consulting. Lyle's worked on all sorts of production lines, from crude processing to fertilizer and utilities. He's a chemical engineer by training, and he went deep into metallurgy with Sherritt. First with zinc, and now mainly with nickel, but also platinum and copper over the years. He's been all over the world setting up commercial plants and processes. He's also a fellow Hurton Albertan, hailing out of Canada's Texas. So that's kind of how I ran into him on LinkedIn. So yeah, thanks for joining me today. I'm glad to have you with us.
Thanks, Al. It's a pleasure to be here.
Yeah, cool. So I first heard about Sherritt while learning about value investing around 2013 in my first job. And I was kind of doing it in the evenings, and it showed up as a screener search with a really low price to book ratio at the time. I was surprised, notwithstanding what was going on with Sherritt at that time, I was just really surprised to find out there was a company like that operating in Alberta, because there's not really too many nickel deposits, as I know. I think they were doing stuff in Cuba at the time. I'm just curious if you have anything to say about what it's like at Sherritt or doing nickel processing in Alberta.
Sure. So, the Sherritt history goes back a long, long time, but the core nickel stuff started with the discovery of a mine in Manitoba when they were looking for additional copper deposits. And in order to exploit that mine, they weren't able to sell the concentrate to the incumbent producers in Ontario. They had their own material. And so Sherritt went and developed its own process using researchers from Canada and the US. And a key ingredient for that process was the ability to get ammonia, which is made from natural gas. So ultimately, they decided to set up the refining end here in Alberta because we have abundant natural gas, cheap, ready to use. And, that was the 1950s, and 70 years later, that refinery is still running. The mine is long closed, as mines do. But yeah, they're now still working off Cuban feeds. And they've built that metallurgical knowledge into many, many different businesses over the years, which came and went and got sold off. And when I joined in 1993, they were doing lots of different things: fertilizers, metals, specialty chemicals, specialty products, advanced manufacturing. Now it's more of a core nickel and cobalt commodity company, and all the other things are owned by other companies.
The one in Manitoba, was that Flin Flon by chance?
No, Flin Flon is a zinc mine owned by Hudbay. It was the Lynn Lake mine that Sherritt
Uh,
operated from 1954 till 1976.
okay. So even by the 70s, it was already looking for new sources for to keep its plant running.
Yep. And when you have a refinery in the middle of a big continent like North America and you're looking for commercial feed globally, it's a tough life. It
Right.
was a difficult operation to keep going from the mid 1970s until they struck the joint venture with the Cuban state in the early 1990s.
Cool. So most of my audience is not metallurgical, chemicals oriented sort of people. So I'm going to try and keep this high level and fun. So, and I've been in Asia for a number of years now, so follow a lot of Eastern sort of culture and history. And like the ancient martial artists and doctors of the East, the metallurgy world is a showdown between two mortal enemies, fire and water. So, having read your stuff, I know which camp you fall in, but why don't you tell the audience, are you a pyrometallurgist or a hydrometallurgist?
Well, my background is definitely hydrometallurgy. Coming out of the shared organization, that's what we did, what we do. But for different ore types, there are different solutions. And pyromet is a great solution for some types of ores and some processing methods. It's far better than using hydromet in some cases. Different ores, different treatment methods. I got to acknowledge that both need to exist, and the future depends what we dig up in the future, what processing methods we'll use. A lot of the time we use both. We use pyromet and then we use hydromet in as we go through the entire process.
Okay. And another thing that you mention in some of your materials is that one of the real stories of the last decade or so has been the emergence of nickel pig iron in Indonesia, which I think is done through pyro. Is that right?
That's correct. It's basically taking the entire ore body, digging it up, and putting it through dryers and kilns and a big furnace to recover iron and nickel as an ingredient for making stainless steel. It's a simple process. The Indonesian and Chinese alignment has figured out how to do it very repeatably, and it's now one of the world's dominant supply sources.
Yeah, and I don't know what the numbers are for nickel, but I like groups like manganese. When it comes to steel, steel's like 90 something percent, and like when you get into batteries, which is the area that I follow more closely, you're like barely 1% of the market at the moment. So for groups like nickel pig iron, like that, if it's going into steel, that's totally fine. But with batteries, that's not going to fly.
That's right. The nickel business is about two-thirds into stainless steel overall for nickel products and about one-third into a range of products that require higher purity. So that might be, nickel alloys that are used for corrosion resistance, much more pure than stainless steel, or batteries and chemicals, uses like that. So, we have a growth paradigm in the market where the battery side of things is growing much faster than stainless steel, but both are still growing. And when the biggest part of your market is growing at, say, 3% a year, and a small part is growing at 15% a year, they both still add a lot of tons of demand every year.
Right. Yeah. Fair enough. And I mean, if it's growing at 15% of the year, then that pie shifts, and so eventually it won't be such a low percentage at that time.
That's right. 15 years from now, we'll probably have a 50-50 split of stainless steel and high purity stuff, mostly for batteries.
Right. Okay. But if you were going for battery grade stuff, would you say that the HPAL or high pressure acid leaching would maybe be the more ideal way to do it rather than the pyro approach?
So you can get there through the pyro process with the laterite ores that are present in Indonesia and the Philippines. And the Philippines is no stranger to nickel processing. I'll just take a step back and note that in the 1970s, there was a fairly large nickel presence in the Philippines called Nonoc, and that plant eventually shut down. But Sherritt actually had a lead role in that, and I've known many people over the years who lived in the Philippines working at the Nonoc facility, helping to make sure that it worked well. And that was a pyro hydro facility using a process that will never be built again because there's more energy efficient ways today. You can get there from nickel pig iron through adding sulfur and making a higher purity form called nickel matte that's then refined. But that is, in my view, the more expensive way to go about it. Going through high pressure acid leaching will end up, from an operating cost point of view, being cheaper. And that is now the dominant growth sector in Indonesia, or coming to be the dominant growth sector in Indonesia, is new high pressure acid leaching facilities to make nickel intermediates that will then go into batteries.
Okay, without going through the pig iron stage, you mean?
Correct.
Okay. So then, like, I understand that Sherritt was also involved in a project in Madagascar. Is that sort of a cautionary tale? Like, it sounds like that didn't go the way it was supposed to.
I wrote a piece recently with Greg Wisher, and this got captured a little bit in a recent article by John Emont in the Wall Street Journal, who I talked to quite a bit. The projects that were built in the late 1990s in Australia, Cause, Bulong, and Anaconda Nickel, now Minera Resources, didn't turn out very well. Two of them shut down. One took a long time to get to anything approaching design rates. A new set of projects was built in the late 2000s, starting up in like 2011-12 era. Ambatavi in Madagascar, Ramu in Papua New Guinea, Goro in New Caledonia, Ravensthorpe in Australia, all of which were very problematic as well. They're all, many of those are still running. Ravensthorpe kind of turns on and off depending on nickel prices, but they've all been financially, they were not good outcomes. But the Chinese built Ramu in Papua New Guinea and persisted with it through a very long startup, 5 or 6 years, to achieve design rate, which would have crippled any Western company. And we saw that with Ambatavi, with Murrin in Australia, with Goro in New Caledonia. The ability to finance a project through a 5 or 6 year startup is incredibly difficult, and that sinks companies. And so nobody's built a second one. And what the Chinese have now done is, persisted and figured out the problems with Ramu and designed a new generation that is frankly not very different, but they've trained thousands and thousands of engineers throughout the supply chain on what exactly they need to build, how exactly they have to put it together, and how exactly they have to run it. And the new facilities that are being built are very successful. Right. The only other company that's built more than one of these is Sumitomo Metals Mining in the Philippines, with the 2 trains at Coral Bay and the Taganito facility. And Taganito worked much better than the first train at Coral Bay. Right. They learned as well.
Okay. Yeah, lots to think about there. How would you characterize the carbon intensity of all that, sort of where things have sort of settled for the moment?
So, I wrote a white paper with a UK life cycle group called Minviro a year ago that went through a bunch of the different processing technologies. There's no question that going to battery grade via nickel pig iron in Indonesia with coal-fired power and coal required for the chemistry in the furnace is a very high carbon route to go. The nickel resources that we have in Canada, Russia, the sulfide nickel resources in Australia, South Africa, are much lower carbon intensity to get through into battery products, because the sulfur that's embedded in them is a form of fuel. You burn sulfur, you make energy. So when you smelt these in a pyromet process, you end up getting energy out of it, and that helps offset the amount of energy you need. And then most of these regions have fairly clean electricity grids, South Africa withstanding. And so what we see is that the carbon intensity for those sulfide mineral products is much, much lower than going through the pyromet on nickel, on the nickel laterites. The high pressure acid leaching is kind of an intermediate process. It really depends on choices you make around your power system and your acid system, because you need to supply a very large amount of sulfuric acid to these facilities. The way it's being done in the Philippines right now is the acid is brought in as a liquid chemical from facilities overseas. Simplifies the process, but you don't get the energy value that you get by burning sulfur on site to make your own sulfuric acid, which is what most facilities have opted to do because it's cheaper more complicated. But when you do the analysis, it's like, well, I can save 50 cents a pound of nickel or some number by having my own acid plant. I'm going to go that route. The economics drive it for the most part. And when you do that, those products come out, say twice the carbon intensity of most of the Western world sulfide-based production. So it's not terrible. If the electricity you need is based on coal-fired power, then it's going to be higher. If it's based on heavy oil, it's pretty similar to coal. If you have renewable resources, like they do in some places, PT Vale runs a nickel smelter in Indonesia that's run off hydropower. But all the new ones are run off coal. The ones in the Philippines run off heavy oil. Ramu run off heavy oil. So, it really depends on where you get that energy from.
I guess one of the natural things people would ask is, what if you just start shifting over to solar? How much power are these like gigawatt scale plants that they're needing for these mines, or like 100 megawatts?
Yeah. So, the general rule of thumb is, 8 megawatt hours per ton of nickel for a high pressure acid leach facility. I think I've got that right. I might have to send you a note later. But, for a commercial facility that's making nickel intermediates, something like the Taganito facility at, 30,000 tons a year, you're probably going to need something like a 30 megawatt power generation facility.
Okay.
It's not tiny, but the real challenge is it needs to run all the time. These are not facilities that you can turn on and off. They need to start up and run for months at a time. And so the challenge with any renewable source other than reservoir hydro is that constancy of power. You can't store enough in batteries to last you all night, every night, and through cloudy days that you get with typhoons. You can't, wind power is sometimes a better capacity factor, but again, it goes still at times. And that's the real challenge with renewables across the mining industry.
Right.
What we're seeing adoption, some significant adoption of renewables in the mining industry is merely to offset the cost of fossil fuels. And they're putting in wind turbines in northern Canada and solar facilities in Australia and Africa in order to burn less diesel or less heavy oil for power. But they still have that power plant because they need the power 24/7, and they just change the operating rate day and night in order to accommodate the power that they're getting from their renewable sources. It's just an operating cost play.
Right. Without disrupting the flow, because I'm sure turning those reactors up and down is not very good for the way they operate or the yields or any of that.
That's correct. It's startups and shutdowns are the most damaging times for chemical process equipment. They like to run at steady state.
And how about I have a feeling this is probably pretty early stage, but there's microbe, and even they found some plants in Indonesia, trees that they've been able to burn the leaves off and get a certain amount of nickel out of. Have you seen some of that stuff?
Oh, absolutely. Phytomining. It's kind of like bioleaching with bugs, but you're letting these hyper-accumulating plants extract nickel from the soil, accumulate it, and there's no question it works, right? It absolutely works. But when you look at it from an economic lens, it, in my view, looks like a bad choice. If you have a deposit of nickel laterite ore, and you've paid money to get this deposit, you want to get that money back. And phytomining is a slow process. So you might be able to do it in a very sustainable manner over hundreds of years, or you can dig it up and ship it to a smelter and get your money back in 10 years. Most business people are going to choose the latter. The phytomining, although it's technically viable, just is such a slow process that to get the tons we need for the critical minerals energy transition and to get the tons that you need for the cash flow to run your operation, it just doesn't really work. Where I see it has substantial potential is in tailings reclamation. We have low-grade materials that you're not going to process through high-intensity means, or that you've already processed and left some material in, because no processing technology gets 100% of the material out. You could then use phytomining to slowly clean up that waste material over decades and, recover a little bit of value and clean up the waste so that they are less impactful to the environment. And that seems like a perfect place for both phytomining and some of what they're now looking at for biological treatment of mine wastes as well.
So does that mean like the trees that pick up these metals selectively also pick up some of the other kind of like waste byproducts that are polluting? Or is it mainly in the metals?
So metallurgist, not ecologist.
Sure.
It's the real problems with the pollution from these waste materials is the metals, the heavy metals.
Okay.
Now, do they pick up more than just the nickel? I'm not sure, right? But the real problems that we have are, what we call the heavy metals, especially, things like chrome, which can exist as chrome 6, hexavalent chrome, which is quite toxic. Nickel, cobalt have, zinc and copper all have environmental, levels at which you shouldn't exceed. There's been a lot of work gone into finding out what those levels are. It's not zero, right? A little bit is okay. A little bit is necessary for human life. Cobalt is a trace mineral, often added to both fertilizers and animal nutrition products. Zinc as well, necessary for human life. So, the challenge is keeping the contamination contained and recovered so that only an acceptable amount reaches the environment. And, from a nickel deposit today, there's nickel leaching out all the time, whether it's a sulfide deposit or a laterite deposit. It leaches into rainwater a little bit, and that's okay. That's what's been going on for millions of years.
Yeah, concentrations are important when you're getting into these considerations and strategies,
Yeah.
I guess.
The problem with waste materials from something like a high pressure acid leaching facility is that those tailings are very fine because it's material that's being leached into solution in the autoclave and then reprecipitated as a very fine material. And the physical and chemical forms that they're in are often more leachable than the original forms. And so, there's a much greater tendency of them to cause environmental issues. And especially if you have something like the iron ore tailings disasters that we've seen in Brazil and other places,
That
tailings
was with
managed.
tailings pond rupturing, if I.
That's right. Yeah. If a tailings management dam fails, it's a big issue. Even if it's only holding dirt, it's a big issue. If it's holding material that has environmentally damaging properties, it's a bigger issue. It's significant. And, tailings management facilities can be designed well. But, I got to say, when I look at the Ring of Fire area, the Philippines, Indonesia, Papua New Guinea, proper tailings storage is a very difficult issue. There's no question, because you've got tectonically active zones, you've got high rainfall events, you've got these challenges that make it more difficult than it is in, say, Western Australia, which is tectonically very stable. It isn't going anywhere. It's flat and it doesn't rain very much. And when it does, the rain doesn't go very far. So, I've seen the heavy rains in Western Australia. I spent a year working at a facility there. The water sits on the ground for a long time, but you don't have the massive flooding events that carry off across the country like you do when you get a typhoon in the tropical areas.
And you've also been critical of proposals that talk about using hydrogen and like ammonia by extension as a fuel source, like fuel cells and that sort of thing. So what's behind that? What's your concern there?
Well, the beauty of working for Sherrod, I was talking to an old colleague last night about this, who, continually marvels at how much I seem to know. It's, I've had the same experiences that other people have had. Maybe I have a better memory for them. I don't know. But with Sherritt, we ran our own hydrogen production, we ran our own ammonia production, we ran our own fertilizer production, we ran our own sulfuric acid plant, as well as the metals refinery. So you get experience across a broad range of things. Hydrogen is incredibly explosive. It's super light and super leaky, and it's an excellent required material for certain things. We really need it for chemistry. We need it to make nitrogen fertilizers that help keep the world population sustainable at 8 billion. We need it potentially for making steel or other uses, but we don't really need it as a fuel. Using hydrogen, which is so light and so leaky and so hard to compress and to liquefy, and trying to transport that around the world and put it into vehicles and stuff, it's rife with problems. A hydrogen leak outdoors, it's not that big a deal. It disperses in the air extraordinarily quickly. I've dealt with hydrogen leaks. I've dealt with an incident where, a guy cut into a live hydrogen line and it exploded. And he got scared, but he didn't get hurt because it dissipated so fast. But would I want it in my house? Do I want it blended into natural gas and piped around the country and put in my house to burn in my furnace? No, I absolutely don't, because I've seen how quickly it leaks through, threaded fittings, the screwed fittings that you have on water lines and gas lines and things like that. It'll leak through the threads and it will accumulate in an enclosed space. So it presents a risk that needs to be addressed. And why would we take that risk if we don't need to? Ammonia, similarly, it's not very explosive. It's not very flammable. It doesn't like to burn, so it doesn't present a big explosion risk, but it's super toxic material. Working in a refinery where, the leaching chemistry was based on ammonia in solution, everything smelled like ammonia all the time. And I've seen the impacts of people who've been exposed to it. It's not good. So putting it in a confined space, bad idea. Burning it in a ship engine, bad idea, because a leak in a ship engine room is going to be very problematic. It can be dealt with extraordinarily safely by trained people. We used to sell anhydrous liquid ammonia out of the Sherritt facilities for use as fertilizer in fields. Farmers would inject it direct into the fields. The people that load it into the trucks wear proper protective equipment, including respirators and stuff, in case there's a leak. And when they disconnect the hoses, there's always a bit of a leak. Pressurized trucks go away. It's like shipping propane. It's not that dangerous contained in a truck. The pressure is not that high. And then the farmers inject it into the fields, through something that's sitting 50 feet behind them as they drive the tractor. That all works pretty well. But when you get it into the enclosed spaces, it's problematic. So, when we have ammonia-based refrigeration systems, which we have for ice rinks and things here in Canada, you sometimes have problems where there's a leak and an exposure and somebody gets injured.
Yeah, Zambonis are often, is that right? Zambonis are powered by?
They're usually propane powered, but the refrigeration system they use to make the ice often uses ammonia.
Okay.
There was a leak in one in BC about 10 years ago that was pretty significant. And, it was a leak inside the room where the refrigeration equipment was. And the guy who went in to deal with it wasn't prepared for it. And, you have a problem. If you're prepared for it and you have the right equipment, it's like any other material that could cause you damage. You just need to be exposed. Firefighters deal with dangerous stuff all the time. Doesn't mean I want the fire in my house. The other thing to remember about both hydrogen and ammonia is when you burn them, so if you put them in a turbine, for example, or an engine and burn them, so they create more nitrogen oxides than burning fossil fuels alone. The hydrogen, because it drives a higher flame temperature, the ammonia, because a part of the ammonia, when you combust it, makes NOx, and that those nitrogen oxides are urban air pollutants that cause damage to people and vegetation. And so do we want that? Is it okay to do that at an industrial power facility? Perhaps, that's removed from an urban environment. But do I want it spread throughout my urban environment? No, not necessarily. So I have big problems with those technologies for those uses. I have great respect and admiration for, the what we've figured out we can do and done over the last 100 years, making hydrogen, making ammonia. It has revolutionized our world, and it's very necessary for the chemistry that it enables, both feeding people and other chemical processes we use. It's just a shame to waste them as fuel.
Well, I mean, it really goes into a lot of fertilizer, and thinking of fertilizer as a source of fuel or energy is it's a pretty reasonable way to look at it as a product. I know a lot of people kind of think of food as fuel, but the amount of fertilizer that's required to grow the amount of food that we do, to consider that in the equation when you're talking about how do you allocate these resources, I think is.
That's right. So one of the things that I talk about in this, Al, is, a concept that I used to use when I was talking to government a lot about highest and best use. What's the best use for methane, natural gas? Well, it's not burning it for heat. That's a good use here in Canada where it gets to -30 in the winter. Burning it for heat's a really good idea. I like not freezing to death, but using it to make fertilizer that feeds the world is probably a better use, right? We have other ways to heat things. What's the best use for hydrogen? Well, it's making that fertilizer, right? And the other chemical uses, the fuel uses, they're just not as important. It's not the best use for the materials. So the hydrogen ladder produced by Michael Liebrecht is, really a nice depiction of where we should prioritize using these rather scarce resources, and where we should, think about, maybe someday if we had an absolute excess, sure, but today we don't. And making hydrogen, making ammonia is not a clean process today. Maybe one day it will be, but it's not there yet.
Germany's really feeling the pain when it comes to ammonium right now, isn't it?
Well, they've bet big on hydrogen, as has Japan, and it's going to be a challenge for them.
I guess the times that I hear it coming up in the circles that I run is more in the fuel cells rather than mixing it in with gas lines or whatever. There's not too much gas heating around here. Though on the other hand, I do see technology companies coming in basically saying they're going to kind of bubble it into the fuel and supplement a fuel of internal combustion engines, sort of like mixing hydrogen into the fuel. And some have even claimed they would go to fully hydrogen, but using an internal combustion engine rather than a fuel cell. So I guess you're kind of running into the same. Well, I'm sure they would have very dedicated hydrogen tanks in that case. I don't know that much about it, but that seems to be a popular tech that people are talking about at the moment.
People like to talk about using hydrogen as a fuel, whether it's for fuel cells, which are electrical devices, or for burning in a dedicated engine. Like, they work. There's no question. They work. They're just inefficient. Making hydrogen from electricity is an inefficient thing to do compared to using the electricity directly. So where you can directly electrify, it will always be cheaper and easier. We have electricity grids all over the world, not all through rural Philippines, right? Not all through rural Africa, but in general, we have, well-distributed electricity grids that supply that energy to most parts of where people live. We don't have networks for hydrogen. And the idea of building hydrogen fueling stations, like, it's been tried. California bet big on hydrogen 15 years ago, and their hydrogen fuel cell fleet is almost gone, and their fueling stations are almost all gone. Most of the cities and countries and regions that have bet on hydrogen buses, hydrogen trucks, hydrogen trains have seen them not work out very well. A guy that writes a lot on that is Michael Barnard from Vancouver. I'd encourage your listeners, if they're curious about the future of hydrogen as a fuel compared to direct electrification, to check out some of Michael's writing. It's very clear and very informative. I have a ton of respect for him.
Is Ballard still running? They were a bit of a Canadian icon tech company for some time with buses and stuff.
Yeah, no, I believe they're still around. And, like, hydrogen was going to be the future of transportation 25 years ago. And they're talking, it's going to be the future today. It's like fusion, right? Fusion is the future of energy. It's just another 20 years away. Yeah, in the meantime, let's solve today's problems. And that's why you're seeing electric vehicles become such a dominant selling feature, whether it's, cars, trucks, trikes, scooters, bikes. I have two electric vehicles. They have a total of four wheels. They're both bikes with a total of 1 kilowatt hour of battery on them, and they work great for me for getting around the city, right?
In the
My car
summertime.
is still gasoline,
Okay.
right? My next car might be electric. I don't know. We'll see when it is that I need it. 5 years from now, I might buy an electric vehicle. Today in Alberta, I'm not sure I would. The charging infrastructure isn't here.
Yeah, the one very different thing about the Philippines compared to Canada. I mean, I did so much road tripping around Canada when I was younger. Like growing up in Prince George, everything was hours and hours of driving away. But I mean, there's times that you can walk across Manila faster than you can drive across it, and a lot of people are doing less than 10 kilometers round trips. Most like 90% of their days, they might do a trip out of town from however often. But the range anxiety situation affects a very different like in terms of like the percent of the population that are affected by the whole range anxiety thing. Very different in Southeast Asian countries compared to Canada, compared to what I grew
Absolutely.
up in.
I'm curious, Al, do you have what we've seen pop up in Taiwan with the battery swap stations for electric scooters in the Philippines?
Yeah, yeah. Gogoro is that the Taiwanese company. They've been on the Nasdaq. They got on the Nasdaq in like 2020. We per like our group has been doing battery swapping from day one, even when we are using lead acid batteries. We didn't do so well in the pandemic, so we kind of had to do a whole bunch of getting back to square one over the last few years. But we are in the process of launching our next pilot, which is basically ramping up to what we see as the next generation of swappable batteries for tricycles of this size.
Nice.
So I was hoping that we would have already had them running a couple months ago, but permitting and whatever, all of these different sort of things, logistics, and so I'm at this point. I think we're in good shape to have them running before the end of the year.
That's excellent. For a crowded urban area, where people don't necessarily have the infrastructure at home to be able to charge batteries that are a little bit bigger than an e-bike battery, they make a lot of sense, right?
Yeah,
It's a physically, one person can handle the battery. It's reasonably straightforward. The battery swap stations they have for taxis and trucks in China are wonders of engineering to me. I
yeah.
don't think you're going to see that roll out across the globe, but it fills a niche.
Yeah, I mean, I've actually the listeners won't be able to see it, but I've got a couple of the tricycles right here, and that's kind of getting into the limit of where you would conveniently do it by hand, like what you're talking about. That's all done via machines and robotics and
Mhm.
hydraulics and stuff. I mean, we could do this. There's lots of ways we could save the labor on doing it by hand as well. But I mean, it's not over. It's not like such a huge burden to move these things in and out. Yeah, but you wouldn't be doing it for much bigger vehicles than this, I don't think.
Right.
So then at that point, if you are trying to commit to a swappable, like smaller swappable batteries like this, then you're starting to need to have more complex power electronics and stuff that allow you to do the daisy chaining and stuff, which is coming. But then you need then you start getting into standards and are people like different companies intercompatible and all that kind of stuff that automotive companies don't traditionally work that way. So are they going to
Yeah,
do it in this case? Hard to say.
that's right. Well, this is one of the challenges with, the transition that we're going through. The fossil fuel era that we're slowly winding down has been pretty straightforward because, plus or minus some quality differences. Coal is coal, oil is oil, gas is gas, petrol is petrol. And it's, you can burn anybody's petrol in your engine, you can burn anybody's oil in your boiler. You don't really care. But on the battery side, the rapid evolution of battery chemistries is, particularly challenging for people that want to justify building new mines and processing facilities. What's the demand for element X going to be 5 years out? Don't care. It takes me 5 years to build a mine. What's it going to be 20 years out? Well, that's really a bit of a different question because the chemistry is quickly evolving. Are we
Right.
going to go to lithium sulfur batteries that don't take nickel and cobalt? They've been playing around with them for a long time. I don't see them coming to be the dominant form in the marketplace in any time soon. But these threats deter investment. And the same holds true on the recycling end. Chemical recycling of batteries to recover the valuable ingredients is entirely doable, and it is being done. But the way you design a plant to recover, say, nickel, cobalt, and manganese from a 111 battery that they built in China 6 years ago, and an 811, that high nickel battery that they build today, they're not necessarily the same facility. And so, again, like when you're going to design and build a facility, you have to know what it's going to do. And retrofitting it on the fly is pretty challenging to deal with
Yeah.
a new chemistry that's going to come out that we don't even know yet. Or, the 811 batteries that are going to hit the recycle stream, say 6 years from now, but aren't there today.
Right. Or like, so the 811 being like 8 nickel to 1 and 1 manganese and cobalt is what you mean, right?
That's correct. Yes.
Which is the highest amount of nickel in, but even that was like an evolution, and it was much higher cobalt and manganese before that, and those metrics are constantly adjusting. So even in the case where NMC is the main sort of feedstock to these plants, the variability will be changing, and like stuff will be coming offline at different times. So those recyclers are going to have to roll with the punches to some extent and be able to handle the feedstocks changing on weeks
Absolutely.
or months or perhaps
And
even
and they
daily.
need to be resilient to unexpected materials, right? The problem in the scrap business is, when you scrap a stainless steel pipe, you know what the stainless steel is, but what's inside the pipe, right? What
Mhm.
crusty stuff is in there that might be bad for your process? You know,
Electrolytes, coatings.
Absolutely. On the battery side, what happens if you design a facility for recycling nickel, manganese, cobalt batteries and some scrap dealer slips a few iron-based batteries in there because he's getting paid the value of the nickel for them because it's done by weight. And now you got iron and phosphate in your nickel cobalt circuit. How do you deal with that?
Right.
The challenges in post-consumer recycling are huge.
Yeah, and I remember in one of your documents you mentioned about in cases where they're using hydrochloric acid instead of sulfuric acid, especially inland. I think you said it's a challenge dealing with the effluents, which
Correct.
was curious for me that it's like, okay, but if you're not inland, you're by the coast, it's not a big deal. Like I mean, obviously salt is chloride. Does that somehow imply that dumping chlorine effluent into the ocean is a
Absolutely.
big deal? Or I was curious about that.
Well, I mean, is it a big deal? Again, not an ecologist,
Sure.
but it's not. It is fairly regular practice to dump what relatively benign effluents into water bodies. And if you're in the middle of a continent, or if you're in the Amazon, and it's all fresh water, you don't want to be filling that up with chlorides and sulfates. If you're on the coast, the ocean is a high chloride environment. So putting some sodium chloride or magnesium chloride or something like that into ocean waters is, from my point of view, it's not that bad. If it's contaminated with a bunch of other stuff that is toxic, okay, now you got a problem. But sodium chloride and magnesium chloride are not toxic materials, but you sure don't want to put them in the Great Lakes.
Sure. Okay. Gotcha. Because I've heard similar statements about sodium effluent from battery recycling.
Right. Sodium sulfate, which gets dumped en masse in some Asian facilities. There's a facility that was built in Finland that was going to have a sodium sulfate effluent, and they ran into permit problems, and they're still looking to solve them. I don't think the facility has run yet. and it's because environmental groups are raising a fuss about the disposal of sodium sulfate even into the ocean, which is pretty common in other places, but it's a problem there. And I think you'll see the same problem in North America. If you want to dispose it into the Mississippi, that's going to be bad. If you want to put it into the Gulf of Mexico, maybe that's accepted. Hard to say.
Cool. So you've also mentioned a couple companies that you're involved with, and we definitely at Paglala Ag we like to talk about entrepreneurship. So you said one about making electricity from waste pressure in natural gas transmission systems. That kind of sounds like a Bitcoin play to me. I don't know if am I close?
Well, no, actually, you're not. I get the reference. The reality is when we want to pump liquids and gases across the country, and this is probably not done very much in the Philippines, small island nation. But when you look across Europe and North America, we have all these big natural gas transmission lines where we pressurize the gas using electricity or gas-fired compressors to something like 900 psi, stick it in a pipeline, send it across the country. And at the other end, it's still at high pressure because we want the pipe to be small, but we burn it in our homes and boilers and things at effectively zero pressure. So we let all that pressure out again. And the standard way that's done is to just put a valve across it and let it expand across the valve. And what you find is the valve gets really icy because it gets cold, but we throw all that energy away that we put in the first place. And it's entirely technically feasible to let that gas pressure down through an expanding device. It's kind of like what we use in refrigerators, right? A refrigeration cycle is very similar. And spin the expanding device, spin a generator, make electricity. It works. The economics are challenging, right? The economics are much easier for, say, doing this with water. It's called a hydroelectric plant, right? Spin a turbine, spin a generator, make power. Water contains a lot of energy when it's flowing downhill. Gases contain less energy, and so the economics are different. It's been done in certain places, but it's not widespread yet. And we're hoping that it will become a more significant player as we will continue to use natural gas for some decades to come.
Oh, and the nickel project in Canada, do you want to mention that or?
Yeah, no, absolutely. I've got a soft spot for this project. Having been in the metals business a long time and having my job at one point be looking for investments in the business. I spent several years with Sherrod and its offshoot companies doing this. I've been watching this project for more than 20 years now. It's the Turnagain Nickel Cobalt project in northern British Columbia, owned by Giga Metals, who, full disclosure, pay me. That's part of my work, along with a variety of other things. And it's a really big, low-grade deposit. And that's a challenge in the nickel business because we have a paradigm of what a good nickel deposit looks like on the sulfide side of things. It's got a bunch of co-products, copper, cobalt, palladium, platinum. It's high grade. Maybe it's underground, but that's okay. We can spend money to mine it because it's super valuable. It's high grade. Over the years, we've seen, and that's like the Sudbury model, the Thompson model, the Norilsk nickel model in Russia. And what we've seen over the years is a continuing evolution to lower and lower grade deposits that then become uneconomic to do underground mining for because they simply don't contain the metal value. But big open pit mines make sense. Mount Keith in Australia, there's the Kevitsa project in Finland. These projects make sense as an open pit mine with lower operating costs. You can tolerate a lower grade. And the ultimate example of this is the copper porphyry deposits that are being exploited throughout British Columbia, throughout South America, where the grades are relatively low, but you're building massive facilities that move huge amounts of material. And if you only make $1 a ton, you're not going to run a mine at 1,000 tons a day and be able to sustain a workforce, but you might be able to at 100,000 tons a day, right? And if you're making 10 cents a ton, you got to be even bigger. So some of these South American facilities, the copper facilities, are moving 500,000 to 1 million tons a day of ore and waste rock. The facility we have in northern BC looks a lot like a copper porphyry. The mineralogy is a little more challenging. The recovery methods are a little more challenging. But from an in situ value point of view, it looks much the same. It will cost about $8 or $10 a ton to process, and it'll be worth about $20 a ton of ore. And so you'll make about $10 a ton. And if you run it big enough, that makes sense. And that's the model for the copper deposits, and it's the model for these new nickel deposits. Getting people to believe that that's going to work is challenging, and doing it in the face of the incredibly rapid expansion of the nickel industry in Indonesia is even more challenging. The market is saturated. And so building a new nickel project in the West is very challenging. And what you see right now is Australia will go from the number 5 producer in the world last year to almost zero production by the end of this year.
Oh, wow.
They will probably drop out of the top 10 because they're closing down all these underground mines, open pit mines, processing facilities. There will probably be 3 mines running by the end of the year, 2 of which ship concentrate overseas, and 1 of which is the high pressure acid leach facility that I helped start up 24 years ago. Still running, and it will probably continue to operate.
Crazy. Okay, well, I'm going to round this off by coming back full circle with my quotes to Back to Fire and Water. So Oscar Wilde said that what fire does not destroy, it hardens. And then, of course, there's the famous one from Bruce Lee, who says, you put water in a teapot and it becomes a teapot. Water can flow or it can crash. Getting back to the whole pyrometallurgy and hydrometallurgy, what do you have as some closing thoughts on that?
There's absolutely a place for both in our world. And, fire is a great method for high intensity processing of certain materials. And it deals with certain elements super efficiently, whether it puts them in slag or off gas or into the products you want. Water-based methods tend to be a little more selective, a little slower. You don't do the same things with fire that you do with water, but they're both necessary for our world. And we will continue to use both types of processing methodologies throughout the minerals industry. There's no question. They both have their place, and they both work very well.
Very cool. How should people get in touch with you if they want to?
Easiest way, look me up on LinkedIn. You can find me Lyle Trytten, or the Nickel Nerd, as somebody branded me this year. And I got to own it. I know a lot about nickel, and I'm pretty nerdy. So you can search for me online as the Nickel Nerd, and you'll find me.
Awesome. Well, thank you very much for joining us tonight. This has been Paglalayag, and we'll sign up from here.
Thanks, Al. It's been a pleasure.